All right, line segments that intersect circles. So we're going to have a bunch of definitions here at the beginning, starting this chapter, dealing with circles. So what I'm going to do is I'm going to give kind of a picture definition of each of these. A circle, let's say I've got a circle here. Most of us know what a circle looks like. And the center of the circle we'll call point C there. We define the circle using symbols as circle, circle, C. Okay, a circle is a set of points equidistant from a center point, which is C here. The center is C, point C. The radius, okay, if I draw a line from the center to any point on the outer edge of the circle, that is a radii. So in this case, CB is a radius. And then a chord is any 2 points, a line that connects any 2 points, a segment that connects any 2 points on a circle. So for instance, if I had that right there, that is an example of a chord. So in this case, actually, let's call this R, excuse me. So we'll call this PR. That is a chord, segment PR. And then a diameter is a chord. Okay, it connects 2 points on a circle. And those 2 points, as well as the middle point, the center point, is the center of our circle. So it's a chord that goes through the center of your circle. That is the diameter, in this case, XY. Now, the diameter has special properties when you compare it to the radius. Most of us know this, but a diameter is equal to 2 radiuses, or 2 radii. Okay. Another way to think about it is a radius is equal to half a diameter. All right. Now let's go on to some other things here. A secant. A secant, these are some terms that most of us aren't as familiar with. A secant is a line that intersects the circle in 2 spots. Okay, it goes through the circle. It's not a segment, it's a line. So DE, if I were to label those 2, DE is a segment, a line. And then a tangent is a line or a ray that intersects a circle at a single location. So if I were to call that point F, maybe this point G, we could say that FG, line FG, is a tangent. Or you could also say ray FG is a tangent. And its point of tangency is where it hits the circle. So this point of tangency is point F. Okay. Let's go see if we can identify these things in this circle. So, okay, we have a circle here with some secants, tangents, chords, radii. So, center of the circle, well, that's the middle here, point A. Okay, excuse me, the center of the circle is at A. And so we name the circle based on its center, so we call that circle A. The radius goes from the center out to the outer edge, so we have AB. Hopefully you paused this and tried this on your own here. Okay. A chord, well, there's a couple chords here. We have NL, also could be called LN, but segment NL. Segment ML, right? Segment ML is also a chord. The diameter, well, that is ML or LM. A secant, well, we have KL is a secant. And since it's a line, we could also call it KN because the line goes on forever, or we could call it LN for that matter. All of those represent the same thing. And then a tangent, in this case, KG. KG is a tangent. It intersects the circle at 1 point, whereas the secant intersects at 2 points. All right. Good. I guess for a radius, we could also say AL and AM if we wanted, right? Okay. I didn't write or here, but these are all or. They don't have to all be said. All right. Let's go through a few more definitions here. Tangent circles. Two circles that intersect at a common point are tangent circles. So maybe think of like a snowman or a number 8. They intersect at a common point. Or maybe think of a circle and then a circle within that circle. Those are tangent circles. They intersect at a common point. Okay, that point is still called a point of tangency. So point of tangency there and a point of tangency there. Concentric circles. Concentric circles are circles that share a center point. There's a circle. There's a circle. We'll call it center point there. Those are concentric. They share a center point. And then a common tangent is a line or segment that is tangent to two circles. Okay, a common tangent. I'll show some examples here in a minute, but in fact, let me give you one example now. I won't leave it on there, but that is a common tangent, that line right there, because it's tangent to both circles. This would be a common tangent, tangent to two circles. Okay? So an example of some common tangents. There we go there, and there. All right. Well, let's take a look at some other pictures here. Two different circles can have up to 2 points of intersection. So let's draw two circles with 2 points. So maybe like a Venn diagram. Sorry about that picture there. That circle doesn't even connect. Okay, so we'll do that one again there. 2 points of intersection. Circles with 1 point of intersection. Well, you could look up there. We have 2 of them right there, but there we go. 1 point of intersection, or all right, once again, I did not close that circle off too terribly well, but there we go. No points of intersection. I guess you could just have 2 different circles. Or you could have concentric circles, right? Share a center point. Okay, we're going to go ahead and move on here. Drawing common tangents for each set of circles, and we have 2 circles that do not intersect, so may help to have a straight edge, and we'll see how my pen does here. It wasn't working too well with this earlier. It's giving me some wavy lines, but all right, a little better. Well, let's assume that hit right there. Okay, we're going to redraw it and give that a shot there. All right, pen seems to be working a little better for me. Okay, so if we have that, that's one common tangent. Okay, you could have another one go in the same direction there, or excuse me, this kind of the same idea, but another direction. Okay, so another common tangent. And then you actually have common tangents running, and let me switch up colors here, it might help out. Oops. That read right through my paper there or my straight edge. Okay, you have a common tangent moving there. And a common tangent right there. All right, common tangents for this next set of circles. It looks like I missed it there. All right, this one has 2 common tangents, whereas the other one had 4. This last set actually has a common tangent. And it goes right down the middle here. Okay, so like so. So it intersects right there. And then we have the common tangents also that run well, I find using the straight edge without zooming in. My screen is kind of weird here. As I seek it. All right, we got that one, and right there. All right, so 3 common tangents there. Well, that took longer than it should, but hopefully that helps out. All right, let's talk about 2 more theorems here. The tangent theorem. A line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at the point of tangency. So if you have a circle, you have a radius, and you have a line that appears to be tangent, we know it's only tangent if it intersects that circle at a right angle. So if we said this was like A, B, and let's call this line L. AB would have to be perpendicular to line L. The external tangent congruence theorem says tangent segments for a common external point are congruent. Okay, so if I have, oh, that is not a good circle. If I have a circle, and it's still not a great circle. I have a circle, I have an external point, say we call that point X, let's call that A, circle A. And then we have a tangent line running from point X, point of tangency at T. Then we have another tangent line. Well, so I actually have that hit. There we go. Through point X at S, we would know that XT is congruent to XS. All right, so applying these theorems, verifying a tangent to a circle, is AB tangent to the circle? So if AB is tangent to the circle, it would have to intersect the radius at the point of tangency at a right angle, meaning this triangle would have to be a right triangle. Okay, well, I know one side of my triangle is 16. I know another side, well, it's like 8 plus 12, so this side is 20. And then this side right here, you got to recognize that this length right here is a radius, and this length is also a radius. And all radii are congruent, so this is 12. Okay, so what I have now, kind of looking at this, I could either do the Pythagorean theorem. I could say AB squared, so that's squared, plus AC squared is equal to BC squared. True. If that's true, kind of like a question mark, if that's true, then it's a right triangle, and AB is tangent to the circle. If it's false, then it's not a right triangle, and since it doesn't intersect at a right angle, AB is not tangent to the circle. But what I'm looking at, I'm seeing some whole numbers here, and I recognize that this is 3 times 4 is 12, and 4 times 4 is 16, and 5 times 4 is 20. So this is a 3, 4, 5 triangle. This is a Pythagorean triple, and I know that 3 squared plus 4 squared equals 5 squared. I know that, so that would also mean that 12 squared plus 16 squared will equal 20 squared. Okay? Just because you're multiplying each measure by 4 there. Okay? So it does work. So yes, AB is tangent. Okay. Well, taking a look at the next one. Is AB tangent? Excuse me there. So, do we have a right angle there? Well, go ahead and take a look. So, AB squared plus AC squared would have to equal BC squared. And we don't have Pythagorean triple this time, so let's check it out. So we know that 6.6 squared plus, so kind of question mark here, 11 squared would have to equal 13 squared. Well, 6.6 squared is 43.56 plus 11 squared is 121. Plus 13 squared is 169. And that gives me 164.56 is equal to 169, which is not true. Therefore, this is not a right triangle, so we'll get rid of you, and the answer is no. AB is not tangent. All right. Very good. Let's apply some other ways here. So, finding the radius of a circle. In the diagram, point B is a point of tangency. Find the radius R of circle C, round to the nearest tenth if necessary. Okay, so we know it's a point of tangency now, which we know means we know it's a right triangle, which that tells us then that BC squared plus BA squared is equal to AC squared. Okay? Or BC, which is R, we'd have R squared plus BA, which is 68 squared, would have to equal AC squared, which this is R plus 28 squared. So multiplying it out, we get R squared plus 68 squared, which is 4624, is equal to, well, R plus 28 squared. If you can't remember, that is R plus 28 times R plus 28, like this, which is R squared plus 28R, so some algebra coming back, plus 28R, plus 784, okay, which is R squared plus 56R plus 784. Okay, so this whole thing equals R squared plus 56R plus 784. Now to solve for R, you have to get R by itself or move everything. You have a quadratic here, so we'll subtract this R over. So when I move this R over, okay, notice that's nice, those cancel now. So now I'm left with 4624 equals 56R plus 784. All right, I can subtract the 784 over, and then I have 3,840 equals 56R. Divide by 56, R to the nearest tenth is 68.6. That means this equals 68.6. Now my class today said, they gave me a hard time, because they're like, that's not even, that can't make sense, because this is 68, that's 68.46. Well, here's your deal. Not to scale. Okay, picture's not to scale. Probably poor labeling of the picture. My fault, I apologize. Okay, this would 68.6 plus 28, that'd be that value right there, or 94.6. That's not what it's asking for. However, it is asking what R is, the radius, and there we got it. One more problem. FG and FH are tangent to E. Find the value of x. Well, if this is tangent and this is tangent, that means they're congruent. They're from an exterior point, tangent to the same circle, so we know that 32 is equal to 8x minus 16. Okay, so 8x, add 16 to both sides, equal to 48. Divide by 8, x is 6. That's all we have. You can plug it in, make sure it works. 48 times 6, or 8 times 6, 48 minus 16 is 32. All right, that's all I got for you. Good lucky.